This specimen being tested is nylon 66. The chemical name for nylon is polyamide, so this can also be called polyamide 66, or abbreviated to PA66 under the drop-down heading. The rate of extension for this polymer is 45 mm per minute. Now beginning the test. Stress whitening is not expected, which is why this specimen is already coloured white. So far, a significant amount of stress elongation can be observed. Now some stress necking is taking place, which is also observed in metals testing. There is the fracture. Depending on the rate of extension, the stress necking can occur in multiple locations within the gauge length area. So you can stress neck at one location, and then a new stress neck point can begin in another location from which it will further elongate, and that can happen multiple times within the same specimen until it does eventually fracture, but it is very rate dependent. From the graph, nylon has a greater maximum load than the polystyrenes, so it is expected to have a higher tensile strength when the calculations are done for its properties. It's got significant elongation here, and the area under the graph denotes large toughness properties. For the nylon and the high-impact polystyrene, just before fracture, they show an increase of force required to maintain the rate of extension. This specimen is glass-filled polyamide 66, a glass-filled nylon 66, so while in the molten viscous state, glass fibres would be laid into it, and then as the mould cooled and solidified, it would take on the shape of the dog bone, which is the standard shape for testing. This will be compared to the standard polyamide 66. Having inputted the relevant information into the software, this time the rate of extension shall be 7 mm per minute. The test can begin now. At present, there is very little elongation. Forces required are over 5,000 newtons. And there is fracture. There is a small gap between the two halves, which indicates there is very little elasticity in the material. Having removed the specimen from the instron, note the fractured ends of the glass-filled nylon. There will be protruding glass fibres at the face, it is very important not to place hands or fingers on those fractured faces. If the fibres were to go through the skin and enter the bloodstream, this would be considered blood poisoning. It's very important when handling glass fibre to always wear gloves. In a specimen like this, as long as the fractured face is not touched, then it's quite safe to handle. The glass-filled nylon is the blue plot, and compared against the green plot of standard nylon, the glass-filled nylon has predominantly taken on the properties of the glass within its matrix, and so it's resulted in higher strength with little ductility. Strictly speaking, the mix between the polymer and the glass fibre makes this a composite material. Nylon on its own has high strength and ductility, but with the glass fibre this changes, particularly in its ability to absorb energy. Therefore, the toughness has been greatly reduced.